Hey, hello everyone. Welcome to today's LeetCode discussion stream for Biweekly Contest 175, which was held on 31st January. We will be discussing all the problems today. Let's move to the very first problem. The problem name is reverse letter, then special characters in a string. In this problem, you are given a string S consisting of lowercase English letters and special characters. Your task is to perform these in order. Reverse the lowercase letters and place them back into the positions originally occupied by the letters. Reverse the special characters and place them back into positions originally occupied by a special character. Return the resulting string after performing the reversals. What does the problem mean? The problem mean that we need to treat the lowercase letters and special characters independently or differently and reverse them at their own place. What do this particular statement mean? For example, these all represent. Okay, let's copy this test case. Say this is a test case. So these are the letters and these are the special characters. All right. Now independently reverse both of them. If you reverse this, it becomes FADCBE. All right. And if you reverse this, it becomes open bracket at the rate hash close bracket. All right. Just normal string reversal. And later, place each of them, that is letters at their corresponding positions and special characters at their corresponding positions. That is, this E will be replaced by this F, this B will be replaced by this A. Similarly, this close bracket will be replaced by an open bracket. What is this? It is a special character. What is the first special character? It is open bracket. What is this? It is E. What is the first letter? It is F. Now again a letter, then A. How is this F and A coming? It is coming from this reverse string. Similarly, this open bracket is coming from reverse string. The positions at which the special characters are present will be replaced by a special character, and that special character will come from the new reverse string formed by us. Alright. Similarly, a letter, so the third letter will be copied. A letter, so fourth letter will be copied. A special character, so second special character will be copied, which is at the rate. Right. And then a letter again, so B will be copied. Right. This is 6. This is 6. Okay, sorry. Here it should have been C, B, then the third special character which is at the rate, then the last letter which is E. All right. And at the end the last special character which is close bracket. So this is how uh, our operation needs to be performed as mentioned in our problem statement. How to do so? So what do we observe till now? We treat letters and special characters independently. All right. That is what we are doing here. All right. Now, if it were and independently reverse both of them. All right. How to do so? If it were a string, what is contiguous string? All right. For example, A B C D. How would you reverse it? you would just run a loop from 1 to half of the size of the string and swap um, the first or the current uh, character with the character at position same position from the end. All right, that is, you would replace the first character with the last character, uh, the second character with the second last character, and so on. Okay, that is what you generally do while reversing a string. But here is uh, the positions of letters and special characters a string. No, it is a subsequence. They are not contiguous. All right, they're not one after another. But here, letters and special characters are non contiguous or subsequence. So how to reverse a subsequence? Let's say we have the position of indices of that subsequence. Let's say it is present at 1, 3, 4, 6, 8, 7, 9, and so on. All right, what would you do? You would run a loop from 0 till uh, the number of elements present in index divided by 2. All right, just treat it like a string. Here we were replacing the first with the last. The same thing will be done here as well. The first index present in the list of indices will be replaced with the last index. All right, so this is the very same thing I am doing right here. I am iterating. Here we were iterating over all the indices, but here I am iterating over only those indices that are present in our subsequence. Find the current index and the index with which it will be replaced. Current index is the value present at uh, current index of idx array. All right, and uh, swap index, that is the index present at same distance from last. One will be swapped with 9. So 1 is first from starting and 9 is first from ending. So swap index for 1 will be 9. All right, idx at n. All right, these are the current index and swap index. What do we do now? Just here I was current index and n minus I plus 1 was swap index. So do the same thing. Swap the current index with swap index. Okay, this is how we will uh, reverse a subsequence. Now, how to uh, partition these subsequence? Our whole problem is uh, pointed down to this problem because we wanted to treat letters and special characters independently. So we need to partition them, right? And after partitioning, we need to reverse the two partitions created. How to partition? If characters are between A to Z, it is a letter. Insert it into the letter array. Else, it is a special character. As it is mentioned in the question that the string consists only of letter and special characters. Alright, so what do we do? What is our final algorithm? It is partition the array into letters and special characters. After that, reverse both these partitions considering them as subsequences. All right. So let's move to the implementation part. Here we are partitioning in this portion. Iterate over the whole array. If it is a character or letter, if it is a letter, that is, uh, it is greater than equal to a and smaller than equal to z, insert the current index into the letter vector, else insert it into the special vector. So just like what we discussed earlier, here this index array, we have two index arrays. The first represent letters and second represent special characters. Now the same code that we discussed earlier, iterate over the values of letter indices and special indices, and then swap both of corresponding values inside the string. At the end, return the string. That is it for the first problem. Let's discuss some test cases more. For example, this test case, if you partition this test case into two parts, one partition will be empty, that is the special character partition, and the letters partition will contain only a single character. So reversing that particular character will give us Z again. In this case, let's dry run what we are doing. For example, let's say this is our string, then what would letter and special look like? Letters and special would contain index 0, index 1, index 2, index 3, index 4, index 5, index 6, index 7, index 8, index 9. Okay, because everything is a special character, and this will be an empty. So reversing an empty subsequence, uh, we would get nothing, and then reversing this particular special subsequence, we would just reverse this particular string. All right, so we would be getting this as our answer. So what is the time complexity of this code? For partitioning the string, we are iterating over the whole string, and the time complexity for this part will be equal to O of n. Later on, for reversing the subsequences, we are iterating over the collected uh, indices. Any of these vectors, letters and special, would not contain more than n elements. So reversing it is again a O of n operation, and this particular portion is again a O of n operation. And what is the overall time complexity? Overall time complexity is O of n plus O of n plus O of n, which is O of n again. And what is the space complexity? We are creating two vectors to store the indices at their space, which is a vector of size at most n. So space complexity is O of n again. That is it for the first problem. Hope you understood it. Let's move to the second problem now. The second problem is minimum k to reduce array within limit. So you are given a positive integer array nums. For a positive integer k, define non-positive nums comma k as the minimum number of operations needed to make every element of nums non-positive. What is non-positive? Either 0 or negative. In one operation, you can choose an index I and reduce nums of I by k. Okay, we can subtract k from nums of I. Return an integer denoting the minimum value of k such that non-positive nums comma k, that is the number of times we subtract k to make every element of nums uh, non-positive, that is 0 or negative, is smaller than equal to k square. Okay, so we need to find such a k. All right. So first of all, let's understand what this non-positive function denotes. For example, nums is this. Let's say k is equal to 2. So now non-positive nums comma k denote the number of moves we need to make this whole array either 0 or negative. For example, for the first index, it is equal to 3. If we apply operation once, it becomes 3 minus 2. Okay, 3 minus k. It is equal to 1. Still, it is a positive number. Then we apply a operation once again. Minus 2, it gives minus 1, which is negative. Then second index. Uh, it is equal to 7. If we apply operation once, it becomes 5. Second time, it becomes 3. Then third time, it becomes 1. Then last time, it becomes minus 1, which is a negative number again. Alright. How many amount of operation have we applied in total till now? For converting 3 to minus 1, 2 operations. For converting 7 to minus 1, 4 operations. Alright. And third index, which is equal to 5. 5 minus 2 is it is equal to 3, minus 2 equals to 1, minus 2 equals to minus 1. Alright, how many number of operations have we applied? Is equal to 3 for the third index. Alright. So what is the total number of operations applied? 2 plus 4 plus 3, 9. And this should be smaller than equal to k square. What was k? K was 2, which is equal to 4. Is 9 smaller than equal to 4? No. So this particular k is not a valid k. And what do we need to find? We need to find the minimum k to reduce our array such that it satisfies this particular condition. That is, the total number of operations applied is smaller than equal to k square. Let's understand few things. Uh, for a particular index and a particular k, how many number of operations need to be applied? Let's visualize this thing. For example, we had a cone, let's say, or a rectangle, let's say, and each time we cut the rectangle by k length. Okay, we removed this k length in one operation. In the second operation, we removed this k length. All right. So, how many times can we remove these k lengths such that it removes the total block. Okay, let's say the length of total block was L. Then we can say that K times number of operations applied is greater than equal to N. All right. And uh, if we write it down, then N is greater than equal to L by K. All right. Because there is a greater than an equal symbol. Let's say if this is a decimal value, L by K is a decimal value, then what would this N means? Because N should always be an integer because it is the number of operations applied. Okay, number of operations can never be applied in decimal times. So if this is a decimal value, it should be rounded up because we want greater values. All right. So N is equal to seal of L by K. Not greater than equal to, it is equal to. N is equal to seal of L by K. So from this, we came to a conclusion that for a particular index and K, the number of operations required is equal to seal of L by K. Now, let's understand what happens as K increases. My claim for time being is that K is monotonic in satisfaction. Generally, when we are asked minimum K or maximum K, these leads to a binary search problem. So that leads to my intuition that K can be monotonic. Let's try to prove it. All right. Okay. Let's try to do it. For each index, as K increases, what happens to the number of operations applied? Since K is in denominator and K increase, the total value decrease. Okay. All right. And since the number of operations required decreases, uh, what is happening with the value of K square? As K is increasing, K square increases. And what is our total aim? Our aim is number of operation minus K square should be smaller than equal to 0. Okay, K square should always be greater than the number of operations applied. Here, this particular term, number of operation, is decreasing, and this particular term is increasing with increment K, number of operation decrease and K square increase. So number of operation minus K square. What happens to this? The positive value is decreasing and negative value is increasing. So overall the value will decrease. Basic mathematics, we can see this intuitively as well. Let's say 5 minus 7, this value 4, 5 is converted to 4, and this value 7 is converted to 8. What happens here? It was equal to minus 2. Here it will be equal to minus 4. Okay, it will moreover decrease from minus 2, it goes to minus 4. All right. So since uh, this particular value decrease, so it has more over chance of being smaller than equal to 0. Okay, so as k increases, the chance of this particular term, the number of operations minus k square, smaller than equal to 0, this particular condition uh, is more likely to be satisfied as the value of k increases. Okay, so if k uh, is equal to t holds, all right, that is the number of operation required for this particular k for t minus t square, it is smaller than equal to 0, then this particular term will increase for t plus 1, and this particular term this particular term will decrease for t plus 1, and this particular term will increase for t plus 1. So this holds as well. So what will our final function be? Some case will not satisfy the requirement, and after a threshold all the case will start to satisfy this constraint. And what do we need to find? We need to find the minimum value of k that satisfies this particular condition for the first time. All right, so how to do so? Since the value is monotonic, since it is monotonic, use binary search to find the optimal value of k. How to use binary search? Find a mid value from a range. If that mid satisfies, how do it satisfy? For all the indices, find the number of operations required for that index, and through this find the total number of operations required. Let's write it down. For a range, find a mid if the total operation for this mid is smaller than equal to mid into mid. Then this implies that answer should be in range low to mid. If it do not, then answer should be in range mid plus 1 to high. All right, and at the end when we are narrowed down to a single value, then print that value, that is the minimum value. So let's see the implementation part, because this particular part was a seal function. So how to implement? Okay, this was a seal function. This was a seal function. How to implement seal function? Keep it in mind because it is used very often. If you convert it into decimal and then find the seal, it is little bit complicated and may give error sometimes. So better play with integer values. Finding seal of n by k, it is same as n plus k minus 1 divided by k. Mug up this formula. If you want, you can go through the proof of this formula as well, but majorly you won't be requiring its proof. Just mug it up because it is very oftenly used. So we talked about binary search. Fix the value of low as 1 and high as 1e4, because uh, the numbers are up till uh, 1e5. What is the sum of these numbers? It is 1e5 into 1e5, 1e10. And what is the number of operations, total number of operations if we choose our value as 1e4? It is equal to 1e6 around. Okay, and what is the square of 1e4? It is 1e8. So this particular value 1e4 will always satisfy uh, the conditions in this particular constraint. If you did not understand what I said, just let us understand it quickly. Total sum of array is at max 1e10, because 1e5 times 1e5, it is equal to 1e10. Okay, now number of operation in this case will be equal to 1e10 divided by 1e4, which is equal to 1e6. And what is square of 1e4? It is equal to 1e8, and this square value is greater than 1e6, so 1e4 will always satisfy. So start the binary search, find a mid, to calculate the total number of operations required for this particular mid, and if this operation is greater than mid into mid, then low is equal to mid plus 1, else high is equal to mid. At the end, if this particular low satisfies the constraints, then answer is low. That is, initialize high as low, and at the end return this high. This was it for the second problem. Let's analyze the time complexity of this particular code. We are writing a binary search. It is well known fact that uh, the time complexity of binary search is O of log n. What actually n is here? You can think that the value of high is n, which is equal to 1e4. And for each computation of binary search, we are iterating over all the elements of our array. So log n into n. At the end, we are iterating over all the elements once again, which is just a O of n operation. At the end, you can say that the overall time complexity is O of n log n. All right. And what is the space complexity? The space complexity, we are taking this numbers as input, although we are using AND operators, so it won't acquire any extra space. But still, let's write it down as O of n or O of 1 if we do not uh, consider these areas our part of space complexity, then it is O of 1. All right, so this is it for this problem. Let's move to the next problem now. So the third problem is longest increasing subsequence with non-zero bitwise AND. In this problem, you are given an integer array nums, return the length of the longest strictly increasing subsequence of n nums whose bitwise AND is non-zero. If no such subsequence exists, return 0. A subsequence is a non-empty array that can be derived from another array by deleting some or no elements without changing the order of remaining elements. So, first of all, let me write down the prerequisites of this problem. You must know longest increasing subsequence in n log n. Like I will be explaining the code for completion sake, but it won't be such a code that you can understand it with basics. I would say that if you do not know that particular code, just watch a random YouTube video on it. There are many random YouTube videos present for LIS code in nlogin. This particular topic is asked in interviews as well, so that's why I'm putting an emphasis on this topic, that watch this particular video uh, before attempting this problem. All right, so what does the problem say? Problem say that we need to find the longest increasing subsequence with additional constraint that bitwise and of that particular subsequence should not be equal to 0. Normal LIS with additional constraint bitwise and of that subsequence should not be equal to 0. Okay, what do uh, bitwise and not equal to 0 mean? It means that there are some some can be written as at least one bit that is set in all the numbers in subsequence. All right. For example, if we have some numbers whose bitwise and is not equal to 0, let's say we have bitwise representation of those numbers like this. Here, since already this bit, and this bit is equal to 0, the final answer, that is final bitwise and, irrespective of what numbers are present in between, let's say we are taking and of four numbers, even if this bit is unset in the very first number, we can say that at the end this particular bit, second bit, will for sure be equal to 0. This fourth bit it will for sure be equal to 0. This sixth bit, last one, will for sure be equal to 0. Alright, what about this one? If we want this one to be set in the final answer, it should be set in all the consecutive elements, all the upcoming elements. It should be set here, it should be set here, it should be set here. Then only it will be set here, this for particular first index. Alright, and since we want our final answers to be non-zero, then one of the bit must be set, and if one of the bit is set in final answer, it is set in all the answers. All right, so we can write it down as, for each bit, all the sub elements which have this bit set form a valid subsequence. All right, what is valid subsequence? A subsequence whose bitwise and is non-zero, and if it forms a valid subsequence, we need to find the LIS of such subsequence, and among those, the largest is the answer. All right, so what is our problem reduced into? For each bit, let's write down the algorithm. For each bit, find the subsequence with this bit set in all the numbers. For all these valid subsequences, find the largest LIS length. All right. Pretty simple to implement if you know the code of LIS. Let's boil down to finding longest increasing subsequence in n log n. for n square code, what do we generally do? We say that dp at index I uh, is equal to number largest length till index I. Now, to calculate dp of I, we need to find max over all j's where dp of j plus 1 is max and j varies from 1 to I. Okay. So since we are varying this j from 1 to I, it is a O of n square solution. What generally happens in LIS? Let's say we got one, we got an array like this: 1, 5, 6, 7, then 2, 3, 4, 5. Alright. Now let's say if we want to make LIS and we are trying to do this greedily. We chose 1 because it is the first number. Then is 5 greater than 1? Yes. So we choose 1 5. Is 6 greater than 5? Yes, it is very good till now. So we choose 6. Is 7 greater than 6? Yes, very good. We choose 7 as well. So this particular array is a valid contender for LIS. But what if we had chosen this one, this 2, this 3, this 4, and this 5? Total length 5, while this was having length 4. All right. Uh, then this gives us error because like the last number was 5, and since we have already chosen 7, 5 is smaller than 7, so it is not a part of valid LIS. So what can we do to mitigate our error? If we can replace this 5, okay, we are going on. We chose 7. At the very first point, we saw 2. This 2 cannot be uh, inserted here. All right. But maybe this 3 can be inserted due to this 2. So, uh, how can that happen? This can happen only when at a particular index, that element contains value greater than 2. All right. Because here 5 is greater than 2. So, 5 restricts 3 from entering. So, replace this 5 with 2. All right. Now this 3 can be inserted. All right. Now insert this 3. Now replace this 7 with 4 as it can be replaced. Now insert 5. So with this construction, we are sure that uh, we are always forming the largest increasing sequence. I repeat that this is just a revision or a reminder of what you have learned in LIS code. Just watch at least one video of LIS from YouTube because it is asked in interviews. So you need to have in-depth uh, concept understanding of that solution. All right. So what is the algorithm for this? Insert the new number to end if you can. If not, insert it at the place which is just greater than the current number. All right. So let's move to the implementation part now. Uh, for each bit, we are iterating over all the valid subsequences. Uh, when is a particular element of subsequence valid? If it has that particular bit set, else just continue. Now, we need to find the LIS. So for finding LIS, create a temporary vector, just like this 1, 2, 3, 4, 5, or 1, 5, 6, 7 we initially had. Now, if uh, find the index of just equal or just larger number greater than equal to current number, because longest increasing subsequence means increasing, not equal to. Okay, so strictly increasing. So here we are using lower bound. Now if we come to a conclusion that no number is greater than the current number in our vector, then it is very good, insert it inside the end, our length of LIS increases in this case. Else, whatever position this particular number can be inserted, insert it. At the end, what do we do? Just replace the current answer with the current size of vector if it is greater than the answer till now. At the end, return the answer. That is it. Here for finding LIS, we are using lower bound and iterating over uh, whole vector. So this particular portion of code is n log n. And this is done 30 times, number of bits times. So overall time complexity is equal to O of n log n into 30. All right. And what is the space complexity? We are creating a vector which can store up to n length element. So overall space complexity is O of. That is it. Uh, let's move to the next problem for now, uh, which is minimum partition score. So the next problem is minimum partition score. It is a really good problem if you want to learn uh, divide and conquer optimizations on dynamic programming. So it is a very famous uh, problem present on CSES. Like if you read this problem, subarray squares, in this particular problem we are given here, just the difference is here we are given the value of subarray is as sum of subarray into sum of subarray plus 1 divided by 2, and here the cost is defined as square of sum of uh, values of subarray. All right, so actually there is no difference between these two problems, because these both of these two functions, that is sum into sum plus 1 by 2 and square of sum, both of them are like quadratic functions, and they satisfy the property of quantangle inequality. All right, which is the core concept of this particular problem, and we will understand it meanwhile understanding this problem. So let's start. It is a really famous DP optimization using divide and conquer. So I would suggest that you attempt at least this CSES problem after understanding this problem. Okay, so let's start. So the problem say you are given an integer array nums and an integer k. Your task is to partition nums into exactly k subarrays and return an integer denoting the minimum possible score among all valid partitions. The score of a partition is sum of values of all its subarrays. The value of subarray is defined as sum of subarray multiplied by sum of subarray plus 1 divided by 2. A subarray is a contiguous non-empty subsequence sequence of elements within an array. Okay, so what do this problem say? We are given a nums and a k. All right, and we want to partition this nums into k parts. So here we want to partition this nums into two parts, such that for each part the sum into sum plus 1 divided by 2 value is minimum. For example, if we partition it into 5 and 1 to 1. Then what is the sum of values? Here it is 25 plus uh, 4. Okay, not 25. 5 into 6 by 2, which is equal to 5 into 3, 15. And here it is 2 plus 2, 4. 4 into 5 by 2, which is equal to 10. So total value is 25. Alright. And this is the most optimal distribution we can have. Because if we take 5 comma 1, then the second subarray is 2 comma 1. Here sum is 6. So 6 into 7 by 2. So 7 into 3, 21 plus 3 into 4 by 2. So 3 into 2, which is 6. So total sum is 27, which exceeds 25. You can think this particular thing like, first of all, uh, intuitively think that value is square of AI or subarray sum. If it is square, uh, think like 10 peoples are standing in a row. Okay, then we need to distribute them into 3 halves, and each of these groups formed will be multiplied by a particular number. All right. Now, the first time number, first person will be multiplied with a number, second person will be multiplied with a number. So, since every person will be multiplied with a particular number, what will we want? We will want that the number with which that person is multiplied to be minimum. And isn't sum that same number? This particular sum denotes the person, and this particular sum denotes the number with which it will be multiplied, because this particular sum can be represented as 1 plus 1 plus 1 sometimes, and multiplied by sum. All right. So this particular person is multiplied with a sum. This particular person is multiplied with a sum. So what will we want? We will want that this particular sum is as minimum as possible. So the product of all the subarray sum should be minimum. Okay, isn't this two things same? It very much is. All right. So let's move to the naive DP approach that you must or you could have had after reading this problem. If we create a state dp of I j as the minimum value to partition prefix 1 to I, such that the number of partitions are j. If this is it, then at the end we need to print dp at n k, because prefix till n represents the whole array, and we want to partition this whole array into k subpartitions or k subarrays, such that uh, the sum of values is as minimum as possible. This is what our dp state is. And if we want to calculate the recurrence, how could it be done? So for calculating dp at I j, we want minimum of dp of m j minus 1 plus cost from m plus 1 to I. Okay, because let's say the very last partition ending at index I start at index m plus 1. Then before this particular partition, that is j minus 1th partition, it should end at index m, and then new partition starts at index m plus 1, which ends at index I. Alright, so this is the recurrence. Now, for this particular idea, what is the time complexity? For this particular idea, our state is O of n into k, and for each of these states, we need to iterate n times in order to fulfill it. Okay, index for calculating index I, we want to calculate index I minus 1, I minus 2, we need to iterate over them. So overall time complexity is n square k. And what is the values of n and k? It is uh, 10 to the power 3 cube, which is too much to pass under these constraints. So it is too slow. So we need to think of some optimization. Although this optimization is not pretty much intuitive, so just uh, continue with me and it would be pretty much understandable at least. And when you see similar problems again, you can handle them on your own. So let's dry run this particular recurrence that we wrote here. For example, here we need to partition this nums into two parts. So 5 1 2 1 at index I. If the very first partition ends, then score will be equal to 15. There are two k's, all right. First k is represent that first partition ends here, and second k represents second partition ends here. This is because there cannot be two partition ending at first index, so it is infinity. I will represent infinity by I, then this, then this one. It is maybe if the very first partition ends here, then zeroth partition should end before the starting of first index, all right, because it is the very first partition. So total value is 5 plus 1 6, and what is the cost for this particular sum? 6 into 7 by 2, so 7 threes are 21. All right, that is what we calculated earlier. And if uh, second partition ends here, then it is uh, the case that first partition should end at index 1. So 15 plus 1 into uh, 2 by 2, which is equal to 1. So 15 plus 1 16. Now for this particular index, if the very first partition ends here, then this is the first partition. So total sum is 8, and 8 into 9 by 2. So 9 fours are 36. And if the second partition ends here, then the first partition could have ended here, that is 5 1 could have been the first partition, and the second partition is 2. Or the second scenario could have been 5 could have been the first partition, and the second partition could have been 1 comma 2. I guess you are understanding what we are doing in this part of recurrence. So if 5 1 was a first partition, then total cost is uh, 6 total cost is 21 to end a partition here, and 2 plus 2 into 3 by 2, which is equal to 3. So total cost would be 24 here. And in the second scenario, 15 plus cost from 1 to 2. So 3 into 4 by 2, 3 into 6, 3 into 2 is 6. So 21 is the second scenario. All right. If the first partition was 5 itself and second partition was 2 1. Similarly, if you calculate for 1 over here, the answer would be 25 as we have calculated till now. All right. That is it. That is the naive n-cube approach, which is too slow to pass. So we need to think of some optimizations. This optimization is not at all intuitive. So bear it with me, and for sure you will understand the uh, concept behind it. So let's say, okay, so if we fix the value of j, okay, everything from now on that we will be discussing will be on a fixed j. All right, just keep that in your mind. For a fixed j, what is j? Count of partition. For a fixed j, if we want to calculate dp of I j, then we would uh, we would have some points. All right, let's say this is a point, this is a point over here, this is a point over here, this is a point over here, this is a point, this is a point. All right, so what do this represent? This represents some z index, this represents some y index, this represent some x index. So dp of ij can be calculated with this formula. And let's say uh, this is the type of curve we get using this particular recurrence. Why so? Because here, as the value of I increases in this portion, from going from left to right, going from left to right, the value of dp I j minus 1, not I, let's say indices are increasing as uh, x or y, or let's say x, okay, increases. Why so? Because uh, what we are saying, dp at x comma j minus 1 represents minimum number of uh, operations, or minimum number of minimum value we get by partitioning prefix till x into j minus 1 partitions. Because we are adding some number, some more number, the dp value will always increase. All right, because uh, initially the burden was of these many elements. If we add one more element into our burden, some of the partitions would have to take up that burden, and overall the total cost would increase due to that burden. So due to the increment of number of indices, due to that particular burden, the value of dp increases. And what about cost? Cost is moreover dependent upon suffix. For this part, if this is the I, then cost would be equal to, if this is the I we are or let's say x we are thinking about, then cost would be equal to the sum of this particular part, multiplied by sum plus 1 divided by 2. Okay, so as the length decreases, sum decreases, and so cost decreases. All right, so uh, roughly maybe this is the graph that is found, because one thing decreases and other thing increases. So in this part, dp uh, dpx j minus 1 is not dominant, cost is dominant. So overall, the total value of this particular term, that is this particular term, sum of these two values, is decreasing because cost dominates in this portion, and in this portion the dp value dominates. So the overall cost is increasing. What do we want? We want the most optimal value of this sum, because we want the minimum one. Okay, we want the minimum one, so we want this most optimal value. Okay, so let's understand one more thing, which is the quadrangle inequality. Okay, so what do the quadrangle inequality denotes? First of all, let's say this particular m, the most optimal m, OPT, is equal to most optimal m. Keep that in mind. So the quadrangle inequality denotes that for these quadratic functions, the if we are given four indices a, b, c, d in increasing order, then the cost of a to c plus cost of b to d is always smaller than equal to cost of a to d plus cost of uh, b to c. All right, let's see this in a number line. For example, these are some points a, b, c, and d. The first cost represent this and this, and the second cost represent this and this. All right, so every time this yellow part will be greater than equal to this red part. All right, so what is the use of this particular thing here? Let's understand it. For a given j, we are always talking about for a given j. All right, I've mentioned it above. For a fixed j, for a given j, as I increases, the value of OPT, that is the most optimal M, what we earlier talked about, this particular term also increases. How so? Let's say, for example, we are calculating dp at I. We are calculating dp at I, and we already calculated dp at j. We already calculated dp at j, and the optimal point for this particular j was this index. So the optimal point for this index I, because I is greater than j, it should be greater than this particular point. That is, it can be this. But if we say vice versa, if this point holds for j, this point is the optimal value for j, then can this point be a optimal point for this I? No. Why? Because this particular cost is included, and this particular cost is included in this particular case. All right. And this is the yellow scenario. And yellow scenario says that cost is always greater if we are going to the yellow scenario. While if we had told that, okay, with the red pen, if we had told that this particular index belongs to j and this particular index belongs to I, then this is smaller. So this quadrangle inequality says that as the value of I increases, the value of OPT, optimal M, also increases. Alright. So let's try to use divide and conquer to calculate optimal value for each index. What do we want? For each index, we want the most optimal value. And if we can find the most optimal value, no need of the recurrence, uh, that is, no need of this n part of the recurrence. Where is the recurrence that we talked about? No need of this n part of the recurrence. We can reduce it to log n most probably. All right. So how to do so? Let's say this is our whole array. All right. And we want to calculate the most optimal value for this most optimal index. And let's say it is found to be this particular index, or let's say this particular index. Do it in O of n. All right. So how many operations have we done? O of n operations to count, to find the optimal point for this mid. All right. Then divide the array that we had into smaller parts, smaller chunks. This is a chunk, and this is a chunk. Now this chunk is divided into smaller pieces. This is a chunk. This is a chunk. If you have studied merge sort, then it might be really clear to you that by dividing these chunks in log n divisions, we have size of 1. All right, each chunk represent a single element. So because we divided into two chunks, we have two new mids now, this particular mid and this particular mid. All right, now what about this particular mid? What is the optimal search space of OPT for this particular mid? It is above. Okay, so since uh, this particular mid had an optimal point here, and according to this theorem, since this mid lies before this mid 2 or mid 1, since mid 1 lies before mid, its optimal point should also lie before optimal point OPT. Okay, so what is the search space for this particular mid? It is from starting this till this point. Now, this particular mid 2, let's say, since this is above this mid, all right, what is the optimal search space for OPT of this mid? It is above the OPT of this particular mid. All right, this is the search space. You can see that these search spaces do not collide or do not intersect. All right. Similarly, for this mid, let's say the optimal point for this one was found to be here. So optimal point for this one is this part. All right. Before the above green part. For this mid, it is above or after this particular point. That is, let's say it is here. If it is here, then for this mid, where can it be? It will be before all the points before it. For this mid, it is having a search space from here to here. Okay, so these lines never intersect. All right, so how many number of divisions we are doing? Log n operations, and in each division we are iterating over all the elements one time, and we find a mid and optimal value for it at the end. Since all the elements are divided into chunks of one size, so we have an optimal point for each of these chunks. All right, and through this we can reduce this O of n k n complexity to n k log n complexity. All right, let's move to the code part so that the logic is more clear. Here we want to divide into minimum number of partitions. The array is given and the value k is given. So initially we want the prefix sum so that we can find the cost in O of 1. All right, so initialize the prefix sum. Now initially the base case is assign dpi of ij for every point as infinity, and another base case, that is one sized partition. One size partition is just equal to the cost of that particular prefix. All right, so create a cost function which is defined above here, total sum into total sum plus 1 divided by 2. All right, so base case is done. Now for each of these case, run the divide and conquer approach by initializing the dpii. Okay, because ith point is the very first point where uh, a partition I number of partitions can be made. Okay, divide every number into one sized partitions, so I partitions are done. So this is a base case here, and using this, run the divide and conquer. In the divide and conquer, we have index, left, right, and optimal left, optimal right. This green part in this particular figure represents the optimal part for this red part. All right. So for this LR, for this block, find the mid. For this mid, iterate over its optimal from its optimal point up till the given I, and endpoint is from mid plus one to endpoint or optimal endpoint, and then over all these points calculate the best value. Then dp stores the best value, and optimal stores the index at which the that optimal index existed. All right, optimal point existed. If there is no optimal point, return. And then, because we found that for index I, the optimal point is uh, opt. So uh, for this new block starting from L up till mid minus 1, we have already found for mid. All right, so we want to find from L to mid minus 1. What is the optimal sequence for it? Because this portion lies to the left of a fond portion, so the initial optimal part uh, is a left bound for it, and the new optimal part is a right bound for it. Similarly, this part, and at the end we have the optimal point for each and every points. At the end, return dp at kn, that is k partitions are done using prefix up till n. That is it. The overall time complexity is O of n into log n into k, as discussed earlier. So that was for the contest of today. All the best for upcoming contests. Hope you appear for weekly contest tomorrow and give your best. Thank you.